Start recording now. Okay. All right, guys. So for today's agenda, when you look on Canvas, you should have seen there's actually kind of two parts today. So there's kind of this really, really short lesson on that just kind of expands a little bit on metallic bonding. So I kind of added that in here today along with our covalent Lewis structures, just because we hadn't gotten to it yet, because we had that day on Friday where I gave you guys kind of like a makeup catch-up day. And so this metallic bonding really, it's actually pretty short. It just goes and talks about some of the properties that metals have, and it explains them using metallic bonding, which is with those delocalized electrons that move around. And so we'll take a look at that. I saw some of you guys have already finished it because some of you guys have already done your little check for understanding. And then really the main part of today is focusing on these covalent bonding Lewis dot structures, because that's directly going to tie into what we do on Wednesday. So today we're going to focus on drawing out these structures and what the chemical structures look like for the covalent bonds. Because then on Wednesday, we're actually going to look like, well, what do they actually look like in 3D? Because when we draw them on paper, they're flat, they're two-dimensional, and so we can't really, sometimes tell a lot about them. But in reality, all of these molecules that have covalent bonds, they're all three-dimensional, so they take up space. And so we're going to talk about what's called the molecular geometry, which has to do with the shapes of the molecules. And so a lot of molecules, depending on their shape, that affects a lot of their different properties. And so, like, for example, water has all of its really, really unique properties. That's why we need it in our bodies and all that kind of stuff. And it's useful for the environment and for other living things. And the reason that water is able to do a lot of the different things that it does based on its properties is because of the shape that its molecular structure has. So that's what we're going to get to on Wednesday. So I'm going to really quick kind of click on the agenda here just to look at it for a second. Oh, we've got a couple more people that have come in. Let's see. Got Jasmine and Alex. Jasmine and Alex. All right. So as I said, there's kind of two parts to today. You're going to describe metallic bonding, and then you're also going to describe covalent bonding and construct those Lewis dot structures for covalent molecules. And so that's kind of what the two questions are for today. Why do metals have the unique properties that they do? So we should be able to kind of answer that. And then how are covalent bonds formed, and how do we draw their Lewis dot structures? So as I said, there's kind of two parts here. There's kind of like a little lesson and a check for understanding on metallic bonding, which I saw that a lot of you guys have already done. And then we're going to look at the covalent stuff. So the metallic stuff, it's pretty straightforward. It goes through here and it gives you several different examples of some of the properties that metals have that we see in everyday life because we use them. And that kind of just talks about why do they have those properties. And it's all based on those delocalized electrons. So it has, here's some metals that we see in our everyday life. Not all of these brass and bronze and steel. Those are alloys. And so those are mixtures of different metals, and they mix them together in order to make them stronger and give them some slightly different properties. Other ones over here, we have aluminum, cast iron, which is just iron that they've literally cast it into a mold to shape it. So that's how they make like cast iron pans for cooking. And copper. So these are all elements, but these are alloys. They're mixtures of metals, but they're all metals because they all have these properties. And so kind of how we use them at home. So this one, there's a light bulb inside. If you ever look inside light bulbs, they do have all these little, they look like wires, but really they're little pieces of metal. They're like filaments. And so tungsten, which is the chemical symbol W, it's a metal element. It's a transition metal, and it has a very, very high melting point. And so because it has such a high melting point, it's ideal to use inside of these light bulbs in these filament materials because they're conducting the heat and the electricity to generate the light. And so the temperature is obviously going to be really hot. If you've ever touched a light bulb, like after turning a light off, it's still pretty hot because it's generating a lot of heat from the energy that it's giving off. So the metal inside there has to be able to kind of conduct that light, that heat and electricity, but it has to be able to withstand a very high temperature so it doesn't melt. And so tungsten is an example of a metal that would have a high melting point. So that's one property that all the metals have. Another one is malleability. So this is where we can like flatten things out into thin sheets. So you can hammer them, press them, or roll them out into thin sheets without breaking. And so aluminum foil, like we pretty much all have this in our kitchen because we use it in baking and cooking. It's a versatile material because you can easily form and mold that aluminum into different shapes, including really, really thin sheets like this. And so malleability is another property that metals tend to have because of their metallic bonding. Ductility, which is the ability to be drawn into a thin wire. And then also this one kind of pairs up with electrical conductivity because the element copper, it's ductile, we can make it into really thin wires and it conducts electricity very, very well. And so copper is used in wiring for houses and buildings and apartments. So anytime that if you're an electrician, you've got to know a lot about copper and these wires and how they all sort of, work together. And it's because of these two different properties. They're ductile, so we can make them into the thin wires and they can fit into all the small places like inside the walls of buildings, but they conduct electricity really well as well. And then kind of the last one here, this is thermal conductivity. So this is different from electrical conductivity. Electrical conductivity is you're conducting the actual electricity. Thermal conductivity is you're conducting heat, okay? And metals are typically good at both. And, metals, typically alloys, conduct heat, which makes them an ideal material for cookware. So cast iron, aluminum are a lot of common metals, but you'll see like there's all kinds of different metals like there's different stainless steel, other things. And so cookware, a lot of times cast iron are these really like dark black iron skillets and iron pans. And they're really, really good at conducting heat. A lot of older people used to use them back in the day before we had like fancy cookware, that you can buy at the store now. Cast iron was kind of one of the first things that they would use to make pots and pans out of for cooking because they knew it did conduct heat really well. And in fact, I still have a cast iron pan, a skillet. It looks kind of like this one over here. It's a little bit taller, I think, but it was actually my grandma. So my grandma passed it down to my mom and now I have it. And so it's really old, but I mean, it's still in really good shape as long as you remember you shouldn't wash it with soap because it does take on the kind of sometimes kind of the taste. So you just kind of rinse it with water and you dry it really quickly so it doesn't rust. And then you just season it, they say, with like salt. So you put salt in it and kind of cook the salt in it. But it gets these really dark colors, and that just means that it's been used a lot. And so it's really good for cooking that way. So this is explaining why the metals have all these properties. So we talked a little bit about metallic bonding the week before last when we did all of our types of bonds. And really this one is just showing you that you have these metal nuclei. So it's the protons and the neutrons in the nucleus, plus it's the inner electrons, because only the valence electrons are the ones that are here moving around. Okay, the metals will give up their valence electrons, and these valence electrons are delocalized, which means that they are mobile. Oh, I don't know what happened to our information. Oh, there it goes. It's a little video. So there is a video here where you can watch a little bit more. It actually shows you an animation with metallic bonding, and so you can see the atoms in the metal, and you can see how the mobile electrons will move around in between the positive metal ions. And then you can also see here, it actually relates to the configuration electron that or electrons, but kind of the technical term is delocalized electrons, because delocalized means that they're not staying in one place. So this slide really connects the two things. So it's going back and it's talking about those properties we saw in the first part, and it's just explaining them using that electron C model with the delocalized valence electrons. So for example, the high melting point of metals is because those positive metal ions and the delocalized electrons that are moving around, they have a very strong attraction. And so if they're attracted to each other very strongly, they're going to resist changing from a solid to a liquid, because when they change from a solid to a liquid, that means your molecules are moving further apart. If you remember back to Unit 1 when we talked about our phase changes. Malleability and ductility, these are kind of explained by the same reason. Because the electrons are delocalized and they're moving around in between, that allows the metal ions to kind of shift, but still maintain the attraction. So when you apply a force, it bends instead of breaking, because the electrons are kind of in between, and so they're kind of acting as like a like grease. You know, they're kind of letting all the metal ions slide past one another without breaking anything. Whereas in nonmetals, that doesn't happen. There's no mobile electrons. So in nonmetals, when you hit it, it's going to break because it's brittle. Electrical conductivity requires charged particles. So you always have to have like positive and negative particles to conduct. And so in metals, what happens is those delocalized electrons are negative. Allows the electricity to flow, and so it will all flow, and you can kind of see in this little picture they're all pointing in one directions. And so when you take physics, you'll learn more about things like batteries and circuits and how those things work, but it has to do with the fact that electricity is flowing in one direction through the substance, and in this case for metals, it's the delocalized electrons carrying that electrical charge. And then the thermal conductivity, it's kind of similar to the electrical conductivity. It requires particles that can pass on, instead of electrical charge, this time it's increased kinetic energy. Kinetic energy is energy of motion. And so when you add heat to a substance and you increase its temperature, that causes the particles to move faster and faster and faster. They have higher kinetic energy. And so what happens is the mobile electrons, those delocalized electrons, they're moving around and they're carrying all that heat, that thermal conductivity. They're passing it on, and so that causes that increased kinetic energy inside the substance. And so you had just kind of a couple little checks here, which I'm not going to go over them because a lot of you guys have already finished it, and then you went on to kind of this next page where this was for your little grade check today, where you had some check for understanding questions on those metallic bonding properties. So not too difficult. It's just kind of related to those definitions that we just talked about. And I saw that some of you guys have already done this one because it was pretty quick earlier. So if you haven't, just make sure that you go and get this done. So there's 10 questions here and you'll go through and then submit it at the end and it'll send me the grade. Okay, so now we're going to focus on kind of the covalent stuff today, because this is kind of not the metallic bonding is not important, but of the two, this is kind of the more important, is knowing how to draw these Lewis dot structures, because this directly relates to what we're going to be doing on Wednesday. So last week we did the ionic bonding, and that involved a transfer of electrons, okay? And so we ended up, drawing those arrows showing the metal transferring its electron to the nonmetal. And then the nonmetal ended up with like 8 dots around it, and the metal didn't have any. And then they had positive and negative charges depending on how many electrons they gained or lost, okay? Covalent bonds are going to be different because if you guys remember, covalent bonds, they're sharing the valence electrons. They're not transferring. It's not like one's giving and the other one's taking. So this is an example of what a covalent bond would look like between two oxygen atoms. So when you have oxygen gas, which is the chemical formula O2, it's 2 oxygen atoms that are covalently bonded. And so what happens is they end up actually sharing not 1, but 2 pairs of electrons. And so it actually makes what we call a double bond. And we're going to look at examples of those as we move through here. But what you need to know is the covalent bonding, they still follow the octet rule, okay, just like the ionic ones. The difference is, though, they obey it by sharing. Because if I count, okay, around this outer ring of this green oxygen, it's got 1, 2, 3, 4, and then it had these 2 green ones, that's 5, 6, but now it's sharing these 2 purple, so that gives it 7, 8, okay? And then if I count the purple oxygen over here, it's got 1, 2, 3, 4, and then it had 5, 6 here from these 2 purple, but it's sharing these 2 green. So by sharing these electrons in between them, they're both still satisfying the octet rule. It's just by sharing electrons instead of one thing giving away and going down to the next inner level and the other one gaining enough to go up to 8 and fill its level, okay? And that's kind of what it says down here. Each oxygen has the original 6, but then they're sharing these 2 between them, which gives them each 8 valence electrons and makes them stable. And again, the only exception, there's a couple of exceptions, helium, because helium, remember, it's on the first row, and hydrogen. Helium doesn't really participate in bonds, but hydrogen does. So hydrogen can only have a complete octet, or it doesn't have a complete octet. It has a full shell with only 2. So when we're going through today, you're going to see that hydrogen can only share 2 electrons, and it can only ever make 1 chemical bond. It can't ever do more than that. There are a couple other exceptions that we're actually going to talk about when we do our shapes next time, but just to kind of introduce it to you guys, the other kind of exceptions are beryllium and boron, so they're kind of right after hydrogen and helium. Beryllium only wants to have 4 valence electrons. It doesn't want an octet of 8. And boron is happy with only having 6 electrons. So you might want to kind of add that in to your notes if you're taking them for day, just that hydrogen is happy with 2, beryllium is happy with 4, and boron is happy with 6. Everybody else is going to want 8, okay? All right, so when we draw Lewis-Dot structures for covalent bonds, okay, these are the steps kind of that you're going to have to follow. So you'll start out drawing your Lewis-Dot structures just like we did with the ionic. But what's going to happen is when the octets are trying to fill, instead of transferring, the electrons are going to be shared. And so notice that this arrow has 2 heads. Okay, in the ionic bonds we did last week, the arrow only had 1 head. It pointed from the metal to the nonmetal because it was showing that transfer. But here, the arrow is 2-headed, or you can draw it with no heads. You can just draw like a line because that's showing me that they're sharing. There's not a transfer from one direction to another. It's just they're joining and sharing together. So what's going to happen in this one is I have a hydrogen and a chlorine, and I can see that this hydrogen has 1 and this chlorine needs 1 more. So that's where they are going to bond up and share. And so it says they share a pair of electrons. And so I draw it like this with the pair being shared in between. And so it says when sharing hydrogen has total of 2, and then the chlorine has 8, because if I were to draw like an imaginary bubble around this hydrogen, it has these 2 electrons that it's sharing with chlorine. And that gives it, that's 2, because hydrogen's always happy with 2. And then if I draw kind of that imaginary bubble around chlorine, it has these 2, 4, 6 that are in green, and then it has the 7th one that it had originally, but now it's sharing this other one with hydrogen. So it has 8 around it as well. So both of their octets are satisfied according to their rules, since hydrogen's that exception. And then what I do is any electron pairs that are being shared in the bond, they turn into this dash or this line. And so that's kind of this last part here. It says each shared pair of electrons, so shared meaning they're shared between our 2 atoms, they're replaced by a dash or a line to indicate that that's a covalent bond. So that's what really makes it different from ionic. In ionic, there were no lines connecting the atoms. We just transferred the electrons and then we drew the positive and negative ions separately. In this one, we are showing the sharing of electrons with a line, and it's connected to form a molecule. And so this one, it says when you count the number of valence electrons, each line, you got to remember that represents 2 valence electrons. So every bond line is a pair of electrons. Okay, see how it was 2 here, and I just changed it to 1 line, and that's called a single bond. Okay, I can have what we call multiple bonds. In covalent bonds, you can have multiple valence electrons, like on the example that we saw here on the first part with oxygen. I told you they're sharing 2 pairs because here's a green and a purple pair, and here's a green and a purple pair. And so that's actually a double bond because they're sharing 2 different pairs. So if I go back here to the second page, here's what they would look like. So hydrogen, they each have 1 valence electron to contribute, so they're sharing 1 pair, and it's a single bond. Oxygen, if we think back to that example on the first page, they're sharing 2 pairs, and so I draw them like this with a double bond. There's 2 lines, but I got to remember each line represents a pair of electrons, so there's actually 4 electrons being shared here. Okay, each line is 1 pair. And then I can have a triple bond, and so triple bonds, typically the only elements that can do triple bonds are nitrogen, phosphorus, and carbon. The only ones that can do double bonds are going to be oxygen, sulfur, nitrogen, phosphorus, and carbon. So you might want to add that into your notes that the multiple bonds, there are only a few elements that can do these. So double bonds, it can be carbon, nitrogen, phosphorus, oxygen, and sulfur, and they're all kind of right next to each other on the periodic table. They're all kind of in group 14, 15, 16. And then the triple bonds, only the ones in group 14 and 15. So only carbon, nitrogen, and phosphorus can do those. Oxygen and sulfur typically don't do don't do triple bonds because typically their electron structures don't allow that. Now, there are some exceptions that they can do triple bonds in certain situations, like when you have ozone, which is 3 oxygen atoms bonded. There's some weird things going on there. But typically, oxygen and sulfur don't make triple bonds. And those exceptions, really, you only learn about those if you do more higher level chemistry after this class. So this is going to actually walk us through the process. Like, how would we draw a Lewis dot structure for a covalent bond? This first example is only going to have single bonds, and then we're going to look at some that might have multiple bonds. So you start off the exact same way as you do for your ionic. You draw the Lewis structure for each atom. So if I look at this chemical formula, there's an N, one N. So if I look up nitrogen, it's in group 15. So it gets 5 valence electrons, 5 dots around it. And hydrogen is in group 1, so it has 1 valence electron, but notice there's this 3 subscript. And if you guys remember back to the beginning of last week when we did ionic, we talked about the fact that in chemical formulas, when you have the subscript number, that tells me I have more than 1 hydrogen. I have 3 hydrogens, so I need to draw 3 separate hydrogens. Each of them get 1 valence electron because that's how many they have on the periodic table since they're in group 1. So then I want to determine the central atom. Typically, there's a couple different ways you can figure out the central atom. It's going to usually be the atom that has the most unpaired electrons. I will tell you, hydrogen will never be the central atom because hydrogen only has 1 single electron. It can only make 1 bond, so it's always going to be on the outside. It's never going to be in the center, okay? So when you're looking at trying to figure out which one is the central, look for the one that has the most unpaired. So in this one, nitrogen has 3 unpaired. So most likely that's going to be the one in the center. And so then I show the sharing of electrons between nitrogen and all 3 hydrogens. So since nitrogen has 3 single unpaired electrons and I have 3 hydrogens, it makes sense that each hydrogen is going to share with one of these single electrons on nitrogen. And that's kind of what it's saying here, is that each hydrogen will share its single electron with nitrogen, and nitrogen will also share its single electrons with each hydrogen. And so I kind of draw those lines connecting them. So notice again, there's not an arrow, okay? It's just a straight line. And then to draw the show the sharing of electrons, I can kind of draw it like this, okay? Where I can see that I have these different colors. Like obviously you guys don't have to draw it in different colors, but this is what it would look like, you know, just to show you guys that this pair of electrons that's being shared, 1 came from hydrogen and 1 came from nitrogen. And so that's kind of what it's showing here, is that around nitrogen, there are 8 valence electrons and each hydrogen has 2, which completes their octet. So if I draw an imaginary bubble kind of around the nitrogen, it has 8 valence electrons, which is what it wants to be stable. And then each hydrogen has 2, which is what it wants. And so then the final thing is we got to make sure that we change each shared pair to a line. And so this is what the final structure for NH3 would look like. Nitrogen's in the center. It's single bonded to each of the 3 hydrogens. And then it has what we call a lone pair. A lone pair means that it's a pair of electrons that didn't bond to anything. And so it's just kind of alone. It's sitting up here on top of this atom, kind of just chilling, just being negative, okay? And that's going to be important because when we do our lesson on Wednesday, anything that has lone pairs, those are actually repelling these bonds because everything, all electrons are negative. And so that affects the shape, and that's what we're going to focus on Wednesday. So it's really, really important that we're able to draw these Lewis structures and we're able to identify how many bonds they have and how many lone pairs they have on the central atom, because that's how we're going to predict and tell what shape it's going to be. All right, so the second one, this one we're doing CO2, which is a pretty common molecule. This is carbon dioxide. So hopefully you guys have seen this, in biology last year with photosynthesis and some other things. And so this one actually is going to have double bonds. And the reason is if I start off just like we did before, I have my carbon with its 4 valence electrons and they're all single. And then I have 2 oxygens because it's O2. And each oxygen has 6 valence electrons because it's in group 16. So again, I start off drawing these just based on the groups they're in the periodic table. And then the central atom, in this one, it's going to be carbon. I will tell you, it does have the most single electrons, the most unpaired ones. But I will tell you, just like I told you, hydrogen will never be the central atom. I will tell you, if carbon is in the compound, it is always the central atom. Carbon always bonds to the most things. And so if it's in a compound, it's going to be the one in the middle. Okay. And then we want to share the electrons showing. So what happens on this one is, if you look, each oxygen has 2 singles. And so if you think about it, well, these 2 singles would pair up with 2 of the singles on carbon, and then that leaves 2 other singles on carbon to pair up with these 2 here. And so what happens is that because each one is sharing 2 unpaired electrons, it's going to form a double bond. So it says here, both unpaired electrons from the oxygen will be used to form the covalent bond with carbon. And in total, the 2 atoms will have 4 valence electrons shared. So both oxygens do that. And so if I draw what it looks like when they're sharing, here is one pair and here's the other pair being shared. And then here's the other oxygen, it's sharing a pair and it's sharing a second pair. So each oxygen is actually sharing 4 electrons with the carbon. And that's kind of what that picture is showing right there. But if I check, they each have a complete octet, because again, if I draw like a little imaginary bubble kind of around this oxygen, it's got 2, 4, and then it's got 6 and 8, the 4 that are being shared. Same thing for the other oxygen. And then if I check the carbon, it's sharing 4 electrons with this oxygen and 4 electrons with that oxygen. So 4 and 4, that's a total of 8. And so even though they're kind of sharing them a little differently, they all still are satisfying their octet rule. And so then I just need to make sure I replace the shared pairs with the lines to show the covalent bond. And so since there were 2 pairs of electrons being shared, it is a double bond, because each pair is a line. Okay, and so on this one, it's actually in a straight line like this. It's called linear, and that's what one of the shapes that we're going to look at on Wednesday. All right, this last one, this one's going to be one that has a triple bond. And so nitrogen and phosphorus and carbon are typically the only things that can do triple bonds. So a lot of times when you have 2 different nitrogens, or like a nitrogen and a phosphorus or something like that, or a nitrogen and a carbon, or a carbon and a phosphorus, you might want to think about looking to see if it can do a multiple bond, because that's typically what will happen. So in this one, we're doing the nitrogen gas, which is N2. So that means I have 2 nitrogen atoms. So I'm going to draw their Lewis dot diagrams. And since nitrogen is in group 15, it gets 5 valence electrons. So I'm just drawing 2 of them in 2 different colors. And if you look, they each have 3 single electrons. Now, here's the thing here. Anytime you only have 2 atoms, there is no central atom. It's just 2 atoms that are going to be connected by a bond. Okay, so that's kind of a tricky thing, is sometimes people are like, well, what's the central atom? Well, in order to have something in the center, you have to have at least 3 things, because you have to have 1 thing on each side and 1 thing in the middle. But since there's only 2 atoms here, there is no central atom. It's just they're going to both be connected by their covalent bonds. So if I look, I'm going to kind of draw them side by side, and it makes sense. They each have 3 singles. And so guess what? All 3 of the single ones are going to pair up. All 3 of those unpaired are going to pair up to each other and create the bond. And so what's going to happen is the nitrogen, they're each still going to have their own lone pair here, but they're sharing 3 pairs of electrons between them. And if I still check my octet rule, they still have a complete octet. Because again, if I draw kind of an imaginary bubble around the green nitrogen, it's got its lone pair, that's 2, and then it's sharing 2, 4, 6. And so 6 and 2, that's 8. Same thing for the yellow nitrogen. It's got these 2 on top of it, plus it's sharing 6 with the other nitrogen, and that's still a total of 8. So individually, they each have 8 around them. It's just they're having to share 6 of them. And so then again, I just replace the shared pairs each with a bond line. And so since there's 3 pairs being shared, that means a triple bond. And that makes sure that everybody has their complete octet and everybody is satisfied. And I haven't, added or changed any electrons. Okay. So your assignment for this today is to kind of practice doing some of these. So it's similar to what you did last week for ionic. It's a Google Slides assignment. So when you look at it, it's going to look similar at the beginning, but then you're going to get to the point where when it asks you to draw the structures or to actually construct and build them, you're going to be following these guidelines for doing the covalent bonds instead of doing the ionic bonds where you had to draw the arrow to show the transfer and then draw the final ones with their plus or minus charges. On this one, you're going to start off with their dot structures and show the connection, and then your final result will be that molecule with the bond lines, whether it's single, double, or triple. So, okay, well, right now it's not responding. I may have to refresh. But if refreshing doesn't work, I may have to log out and log back in. But because I know it was working earlier this morning, so it must be doing something weird now. But essentially the directions on it are really, really similar to the ionic bonds. So if you've already done that one, this one should be fairly easy for you to figure out. I will say there are some practice with single, and then there is some with double and triple. So look for that, towards the end. And then on Wednesday, we're actually going to talk about how these molecules relate to their 3D shapes. And then on Friday, we're going to be kind of doing a review and practice of everything, because then next week on Tuesday, we're going to be taking our Unit 3 test over all of our chemical bonding stuff. So that's all of kind of the electron configurations and dot diagrams and our orbital diagrams. And then it's all these types of bondings, the covalent, the ionic, the metallic, and drawing all these structures. And then also those 3D shapes that we're going to talk about on Wednesday. So, okay, here it is. It popped up finally. So if I click on the title, it's going to open it. You can open it in Google Slides when you click on that, and it'll make a copy for you. And then when it opens, again, you will just follow the directions like you did on the assignment from last week. The only difference is, like I said, when you get to a certain point, it's going to have you do the covalent structures instead of ionic. So the process of doing it is going to be a little different. But it gives you all the different electrons and the bond lines to drag and drop to create your structure on the slide. So I'm going to scroll down to where some of those are. So it'll give you whatever element symbols you need. It'll give you, single electrons and pairs of electrons. And it will give you the single, double, and triple bond lines facing different directions. Just because depending on how the structure is drawn, you might need some that are going up and down, or you might need some that are going left and right. So it has you doing water, which is H2O. It has you doing, I think this one's NCl3. It hasn't popped up yet, but it'll pop up in a second. Then it has you doing CO2, has you doing CF4. And then HCN, which that last one's a little tricky. Got to think a little hard on that last one. Okay. So really you're doing kind of 5 full-on practice ones by yourself. And then the first few slides are just kind of recap of like dot structures and valence electrons and some fill in the blank stuff similar to what you guys had last time. Anybody have questions about today's stuff? So I don't know if you guys I know some of you guys had already done the metallic stuff, but I don't know if you had already started looking at the covalent lesson. So hopefully going through the examples together maybe helped clarify some. If it didn't, then on Wednesday when we do the shapes, we can take a little bit of time to kind of discuss this again a little bit. And then we'll also have some time on Friday when we're working on reviewing and practicing before our test next week. So I'm gonna let anybody have any questions they would like to ask.